The fundamental question of whether we are alone in the universe remains one of the most profound and persistent inquiries in the history of human thought. For decades, the scientific community has dedicated substantial resources, intellectual capital, and technological capability to the search for extraterrestrial intelligence, commonly known as SETI. However, despite these sustained efforts, we have yet to uncover definitive evidence of civilizations beyond our own. The silence of the cosmos, often referred to as the Great Silence or the Fermi Paradox, continues to challenge our understanding of life's prevalence in the universe. Today, we turn our attention to a specific, highly sophisticated strategy that aims to refine this search. This strategy proposes a shift from blind observation to a more targeted approach, predicated on two distinct but interconnected pillars: the rigorous forecasting of Earth's own potential futures to identify specific search targets, and the deployment of next-generation astronomical observatories capable of detecting these predicted signatures. To understand how we might identify them, an advanced extraterrestrial civilization, we must first grapple with the limitations of our current methodology. Historically, the search for technosignatures has been fraught with uncertainty. A technosignature is any measurable signal or spectral marker that indicates the presence of technology, and by extension, a civilization capable of creating it. The difficulty lies in the lack of a reference point. We are currently aware of only one technological civilization in the entire universe, our own. Consequently, our search criteria have been largely anthropocentric, assuming that extraterrestrial entities would utilize technologies similar to ours, such as radio communications or laser emissions. This leads to a significant problem of ambiguity. We simply do not know with certainty what a signal from a truly alien civilization, one that may have evolved under vastly different environmental pressures and followed a divergent technological trajectory, would actually look like. This is where the first component of the new strategy comes into play: motivated forecasting of planetary futures. This concept is detailed in recent scientific literature, specifically relating to Project Janus and studies concerning the future evolution of Earth over the next millennium. The premise is that by modeling the potential developmental paths of human civilization and the Earth system, we can create a catalog of potential signatures that we might then search for in the cosmos. We cannot, of course, predict the future with absolute certainty. The chaotic nature of socio-political evolution, technological breakthroughs, and environmental feedback loops makes a singular prediction impossible. However, we can construct a spectrum of scenarios. This approach involves developing multiple, distinct versions of Earth's future, specifically 10 diverse scenarios as proposed in recent studies, based on our current understanding of physics, climatology, and technological progression. By focusing on these concrete scenarios, we move away from blind guessing. Instead of asking, "What might aliens do?" we ask, "What might Earth look like in 1,000 years under specific conditions?" And then look for exoplanets that match those projected states. This method provides a grounded template for observation. If we model a future where Earth relies heavily on solar energy, we can calculate the specific reflective properties of vast solar arrays. If we model a future of heavy industrialization, we can predict the atmospheric concentration of artificial pollutants. This predictive modeling transforms the search from a hunt for the unknown into a search for specific, quantified data points derived from the extrapolation of our own existence. However, theoretical models are only as useful as the instruments available to verify them. This brings us to the second deficiency in our current search efforts: the hardware limitation. The detection of Earth-like planets, rocky worlds residing in the habitable zone of their parent stars, is an immensely difficult task. The habitable zone, often colloquially termed the Goldilocks zone, is that specific orbital region where conditions allow for the existence of liquid water on a planet's surface, a prerequisite for life as we know it. Identifying these planets is merely the first step. Characterizing their atmospheres to detect biosignatures or technosignatures requires a level of precision that challenges the limits of modern engineering. Currently, we rely on observatories like the Hubble Space Telescope and the James Webb Space Telescope. While these instruments are marvels of engineering and have revolutionized our understanding of the cosmos, they were not primarily designed for the specific task of directly imaging and analyzing the atmospheres of Earth-sized exoplanets orbiting sun-like stars. The contrast ratio required to see a faint planet next to a bright star is billions to 1. To bridge this gap, we must look toward the future of astronomical instrumentation. We must examine the proposed observatories that will succeed Hubble and Webb, machines designed with the specific capability to resolve these distant worlds and analyze their spectral fingerprints. Before delving into the mechanics of these future telescopes, it is necessary to distinguish clearly between the two types of signals we are hunting: biosignatures and technosignatures. The distinction is crucial for understanding the data these future missions will collect. Biosignatures are observable indicators of life itself, implying the presence of biological processes, but not necessarily intelligence or technology. These markers could be produced by simple microbial life or complex flora and fauna. In the context of exoplanetary astronomy, we look for atmospheric gases that exist in chemical disequilibrium. On Earth, for example, the simultaneous presence of molecular oxygen and methane is a strong biosignature. Oxygen is a highly reactive element. In a non-biological context, it would quickly react with other elements and disappear from the atmosphere. Its persistence suggests a continuous replenishment source, which on Earth is photosynthesis. Similarly, methane in the presence of oxygen should degrade rapidly. Their coexistence suggests that biological organisms are constantly producing both. When a planet passes in front of its host star relative to our line of sight, an event known as a transit, starlight filters through the planet's upper atmosphere. Different chemical elements and molecules absorb light at specific wavelengths. By analyzing the spectrum of this filtered light, astronomers can identify absorption lines that correspond to specific gases. We look for oxygen, ozone, methane, nitrous oxide, and other compounds associated with biological metabolism. Beyond atmospheric composition, there are surface biosignatures. One of the most fascinating is the red edge. This phenomenon relates to the reflectivity of vegetation. Terrestrial plants use chlorophyll for photosynthesis, absorbing light in the blue and red parts of the visible spectrum. However, they reflect near-infrared light very strongly to avoid overheating and tissue damage. If one were to observe the spectrum of light reflected from a planet covered in vegetation, one would see a sharp increase in reflectance at wavelengths just beyond the visible red, roughly around 700 to 750 nanometers. This sudden jump is the red edge, and detecting it on an exoplanet would be a compelling indicator of plant-like life. We also consider temporal biosignatures. These are changes in a planet's appearance or atmospheric composition over time that correlate with biological cycles. For instance, the seasonal oscillation of carbon dioxide levels on Earth, driven by the growth and decay of vegetation in the northern hemisphere, creates a rhythmic signal that could technically be observed from space. However, our primary focus in this lecture is the search for intelligent life, which necessitates the detection of technosignatures. These are signals that cannot be explained by natural geological or biological processes, and imply the manipulation of energy and matter by a technological civilization. The search for technosignatures has traditionally focused on radio astronomy, the detection of narrow-band radio transmissions. This approach, pioneered in the mid-20th century, assumes that civilizations will use radio waves for communication, just as we do. But the new strategy outlined in recent research argues for a broader definition of technosignatures, informed by our projections of Earth's future. If we extrapolate the Anthropocene, the current geological epoch where human activity is the dominant influence on climate and the environment, into the future, we can identify other potential markers. Consider atmospheric pollution. An advanced industrial civilization might release synthetic chemicals that do not occur naturally. Chlorofluorocarbons, for instance, are complex molecules used in refrigeration and industry on Earth. They are potent greenhouse gases and remain in the atmosphere for long periods. If we detected the spectral signature of CFCs or similar artificial compounds like nitrogen dioxide in high concentrations on an exoplanet, it would be a strong indicator of industrial activity. Furthermore, we must consider the thermal footprint of a civilization. According to the laws of thermodynamics, specifically the second law, energy use inevitably generates waste heat. A civilization consuming vast amounts of energy, whether from fossil fuels, nuclear fission, or fusion, will radiate that energy away as heat. This would manifest as an excess of infrared radiation coming from the planet, distinct from the natural heat re-radiated from the star. In extreme scenarios, often described by the Kardashev scale, a civilization might construct massive megastructures to harvest the energy of their star, such as a Dyson swarm. Such a swarm would absorb visible starlight and re-radiate it as mid-infrared heat, creating a very specific spectral anomaly. Even the night side of a planet could reveal its inhabitants. Artificial illumination, city lights, creates a distinct signature. If a planet is tidally locked or has a significant night side, the presence of artificial light would be detectable given a sufficiently powerful telescope. This is not just about visible light. The specific spectrum of LED or sodium vapor lighting differs significantly from natural sources like lightning, aurorae, or volcanic activity. This brings us to the Project Janus and the 10 scenarios of Earth's future. The researchers argue that by strictly modeling the next 1,000 years of Earth, we can refine these search targets. Why 1,000 years? It is a time frame that is long enough to allow for significant divergence in developmental paths, but short enough to be grounded in intelligible physics and sociology. In one scenario, we might model a high-growth future. Here, human civilization continues to expand its energy consumption exponentially. We master fusion energy, expand into the solar system, and geoengineer the planet. The technosignature of such a world would be characterized by high waste heat emissions, the presence of exotic industrial pollutants in the atmosphere, and perhaps the spectral glint of orbital infrastructure. In a contrasting scenario, we might model a sustainable equilibrium or eco-state. In this future, humanity prioritizes environmental integration. We stabilize our population, transition fully to renewable energy, and minimize our ecological footprint. Paradoxically, such a civilization might be harder to detect because they strive to be less intrusive. Their atmosphere might look remarkably similar to a pre-industrial Earth, cleansed of pollutants. In this case, the technosignature might be the absence of expected natural variations, implying a managed climate or subtle markers like the specific reflectivity of vast solar farms covering deserts or oceans. There is also the darker possibility of collapse scenarios. If civilization rises and then falls due to war, resource depletion, or climate catastrophe, what remains? The study suggests that even a collapsed civilization leaves a footprint. We might see a planet with the chemical scars of a past industrial age, lingering radioactive isotopes, long-lived atmospheric pollutants, or the debris fields of destroyed satellites, orbiting a world that has otherwise gone silent. To distinguish between these scenarios on distant worlds, we need the second pillar of our strategy, the hardware. We are approaching a new era of astronomy, moving beyond the capabilities of the Hubble and James Webb Space Telescopes. While JWST is a powerful infrared observatory, it relies on the transit method and direct imaging of planets far from their stars. To image an Earth twin, a small, rocky planet orbiting close to a bright star, we need different tools. The first major concept is the Habitable Worlds Observatory. The HWO aims to be a massive space telescope, likely with a primary mirror diameter of around 6 meters or more, operating in the ultraviolet, visible, and near-infrared spectrums. The critical engineering challenge for the HWO is suppressing the light of the host star. The star is billions of times brighter than the planet. To see the planet, we must block the star. There are two primary technologies proposed for this. The first is an internal coronagraph. This is a complex system of masks, prisms, and mirrors inside the telescope that blocks the central light of the star while allowing the light from the surrounding planets to pass through. It requires active wavefront control, deformable mirrors that adjust thousands of times a second to correct for minute imperfections in the optics. The second option is a starshade. This is a massive, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of the telescope. It would physically block the star from the telescope's view. The shape of the petals is mathematically precise, designed to minimize the diffraction of light waves around the edges, creating a deep shadow in which the telescope can operate. This would allow the HWO to take direct images of Earth-like planets, appearing as faint pale blue dots, and perform spectroscopy on their atmospheres to look for the oxygen, methane, and industrial chemicals discussed in the forecasting scenarios. The timeline for the HWO places it in the late 2030s or early 2040s. It represents the flagship of future American astronomy. But it is not the only concept. In Europe, there is the LIFE initiative, the Large Interferometer for Exoplanets. This represents a fundamentally different approach. Instead of one large mirror, LIFE proposes a formation of separate spacecraft flying in precise formation. These spacecraft would work together as an interferometer. Interferometry is a technique where light from multiple telescopes is combined to simulate a much larger aperture. The LIFE mission would utilize nulling interferometry in the mid-infrared range. By combining the light waves collected by the different spacecraft in a specific way, The peaks of the light waves from the star can be made to line up with the troughs of the waves from the same star, effectively canceling each other out, destructive interference. This nulls the star's light. However, because the planet is at a slightly different angle, its light waves arrive with a different phase shift and are not canceled out. Mid-infrared is a particularly interesting part of the spectrum for this work. In the mid-infrared, the contrast between a star and a planet is much more favorable than in visible light. While a star is a billion times brighter than a planet in visible light, it might be only a million times brighter in the infrared. Furthermore, the mid-infrared spectrum contains rich data on molecules like ozone, methane, and carbon dioxide. The LIFE concept envisions 4 collector spacecraft and 1 combiner spacecraft, flying in a rigid formation at the Lagrange point 2, attempting to execute one of the most precise formation flying maneuvers in the history of spaceflight. Moving down from space to the ground, we must discuss the Square Kilometre Array in Australia. The SKA will have a collecting area of roughly 1 square kilometer, hence the name. This massive surface area provides unprecedented sensitivity. In the context of SETI and Technosignatures, the SKA will be a game changer. It will be sensitive enough to detect leakage, radiation from nearby stars. Until now, Radio SETI has largely depended on aliens intentionally beaming a high-power signal at us. The SKA could theoretically detect the background radio chatter of a civilization, their airport radars, their television broadcasts, their telecommunications networks, even if they aren't trying to contact us. It will operate across a wide range of frequencies, scanning the sky with a speed and depth that dwarfs all previous radio surveys combined. Finally, we arrive at the most ambitious, perhaps even crazy, concept mentioned in the source material, the Solar Gravitational Lens mission. This concept relies on the theory of general relativity proposed by Albert Einstein. Massive objects curve the fabric of spacetime, and this curvature bends the path of light. Our sun is a massive object. As light from a distant star or planet passes the sun, it is bent inward, focusing at a point far behind the sun. This creates a natural, telescope-like effect of immense power. The sun itself acts as the primary lens. The magnification provided by this gravitational effect is roughly 100 billion times. If we could place a telescope at the focal point of the sun's gravitational lens, we could achieve resolution impossible with conventional optics. We are not talking about seeing a planet as a single dot of light. We are talking about multipixel imaging, resolving the surface features of an exoplanet. We could see continents, oceans, weather patterns, and potentially the lights of cities or large-scale artificial structures. However, the engineering challenge is staggering. The focal region of the sun's gravitational lens begins at approximately 550 astronomical units from the sun. For context, 1O is the distance from the Earth to the sun. Voyager 1, the farthest human-made object, has traveled for over 45 years and is only about 160 O away. To reach 550 O in a reasonable human time frame, we would need propulsion technologies far exceeding our current chemical rockets. We would need solar sails, nuclear propulsion, or other advanced concepts to travel huge distances quickly. Once the spacecraft arrives at the focal region, it must navigate with extreme precision, staying within the narrow beam of light focused by the sun, while both the sun and the target exoplanet are moving through the galaxy. It is a navigational nightmare. Yet, the scientific payoff would be the ultimate prize. a high-resolution photograph of an alien world. In synthesizing these elements, the theoretical framework of Project Janus, and the engineering marvels of HWO, life, SCA, and SGL, we see a comprehensive roadmap for the future of contact. We are moving from a passive era of listening to an active era of prediction and precision observation. The strategy posits that we first use our understanding of Earth to generate the templates. We define the spectral signatures of an industrialized world, a green utopia, or a post-apocalyptic wasteland. We utilize the 1,000-year forecast to broaden our imagination strictly within the bounds of physics. Then, we construct the eyes capable of seeing these signatures. The habitable world's observatory will scan the nearby stars in ultraviolet and visible light, looking for the chemical imbalances of life and the pollutants of industry. The Life mission will scrutinize the thermal emissions in the infrared, hunting for the waste heat of civilizations. The Square Kilometer Array will listen with an ear spanning continents for the hum of alien radio traffic. And perhaps, in the more distant future, a mission to the Solar Gravitational Lens will send back the first true image of another Earth. This is a slow process. It is a multi-generational endeavor. The predictions of Earth's future help us narrow the search, saving precious telescope time by telling us exactly what to look for. We are not just looking for life, we are looking for mirrors of our own potential timelines. By studying the possible futures of Earth, we are, in a very real sense, learning how to recognize our neighbors. The silence of the universe may not be due to an absence of life, but rather an absence of the specific tools and specific questions needed to find it. With these new strategies and these new machines, we are finally preparing to ask the right questions and hopefully receive an answer.